Welcome to the deep dive. Today, we're really getting into something fundamental, something we use every single second: electricity. How do we actually make it?
Right. It feels like magic sometimes, but it boils down to some core science.
That's what we're doing today.
Hmm.
Unlocking those secrets, from big spinning things to tiny chemical reactions. It's going to be interesting.
Exactly. We'll look at the two main ways, fundamentally. First, generators getting electricity from movement.
Okay.
And second, batteries using chemistry to get electrons flowing. It covers pretty much everything from power plants down to your phone.
Right. Okay, generators first then.
Yeah.
This electricity and magnetism link. It's fascinating.
It really is.
The key thing, as I understand it, isn't just having a magnet near a wire.
No, not at all.
It's about movement. You have to move the magnet or move the wire relative to each other.
Precisely. You need a changing magnetic field passing through that wire loop.
So if the magnet just sits there, even if it's really strong,
Yeah.
nothing.
Nothing. No current. The magnetic field has to be, well, changing, fluctuating across the wire.
Why? What's the change doing?
Well, that changing field actually exerts a force on the electrons in the wire. It gives them a push.
Ah, okay.
Yeah.
It literally shoves them along the path.
Basically, yes. And if the magnet stops moving, the field stops changing, the push stops, and the current stops. Simple as that.
Okay, but a single wire and a little magnet, that's not powering much, is it?
Well-
How do we scale this?
Right. That's where the engineering comes in. Here's where it gets really interesting. You don't use just one wire loop.
You coil it up.
Exactly. You wind the wire into a tight coil. Each loop adds to the effect. It's like having many, many wires all working together.
So more loops, more push, more current.
You got it. And then think about power plants. They take this principle and run with it. Huge scale.
Like with dams and water turbines.
Yep. Or massive wind turbines. They use that mechanical energy, the spinning motion from water or wind, to rotate enormous coils of wire inside powerful magnetic fields. Or sometimes rotate the magnets around the coils. Same difference.
Turning movement into electricity on a massive scale.
That's the heart of it. Transforming kinetic energy into electrical energy.
And how do we, measure this stuff
Yeah.
to know what we're actually getting?
Ah, good question. That's where tools like a multimeter come in. Essential piece of kit.
Right.
It lets you measure voltage. That's the electrical pressure or push.
Ah,
Current, that's the actual flow rate of the electrons.
okay.
And resistance, how much the wire resists that flow.
Got it. And you mentioned AC/DC earlier. That comes from generators too.
Well, generators naturally produce alternating current, AC. The direction of the electron push, and therefore the current, flips back and forth as the coil spins.
Okay, alternating back and forth.
Right, which is actually really useful for sending power over long distances on the grid. It's different from batteries, which give you direct current, DC.
DC is just one direction.
One constant direction. Electrons flow from negative to positive. Think of water flowing one way down a pipe.
So AC for the grid, DC for my phone battery.
Mostly. Generally speaking, yes. We convert AC to DC for lots of devices.
We could even make a simple version, right? Like shaking a magnet in a tube with wire coiled around it.
Absolutely. A shake generator. It's a great little demo. You shake it, the magnet moves inside the coil, changing magnetic field.
And you generate a voltage. Probably tiny, but it's AC.
Exactly. It shows the principle perfectly. You're turning your shaking motion into electrical energy.
Okay, so that covers motion. What are the other big way? Chemical reactions. Batteries.
Right. The chemical route to electricity. So what does this mean for, the power sources we carry around?
Yeah, how does a little battery actually work?
Fundamentally, you need three things. A positive electrode, a negative electrode.
Okay, two terminals.
Yep. And crucially, something called an electrolyte in between them.
Electrolyte,
Yeah.
like in sports drinks.
Sort of the same idea. A substance could be a liquid, a paste, even a solid that allows ions, charged particles, to move between the electrodes. But it doesn't let electrons pass through it.
Ah, so the ions move inside, but the electrons have to go around the outside circuit.
Precisely. The chemical reactions at the electrodes cause electrons to build up at the negative one and be stripped away from the positive one. That creates a voltage, a potential difference. Connect a wire, and the electrons flow from negative to positive through the wire.
Let's take that classic science fair project, the lemon battery. How does that fit?
Perfect example. It's surprisingly simple, but shows everything. Your nail, usually zinc-coated or galvanized, That's the negative electrode.
Okay.
A piece of copper, like a wire or a coin, that's your positive electrode.
Got it. And the lemon juice.
That's the electrolyte. The acid in the juice facilitates the chemical reactions. Electrons build up on the zinc nail, leave the copper, connect them with a wire outside the lemon.
And zap. Well, maybe not zap. A tiny current flows.
A very tiny current, yes. But it is a current generated purely by chemistry.
And batteries eventually die. Why?
Because those chemical reactions aren't infinite. The materials at the electrodes get used up or the electrolyte changes. Eventually, the reactions stop, the electron pushing stops, and the battery is flat.
Does the size of the battery matter for how much voltage it has?
Good point. No, not directly for voltage. The voltage is determined by the materials used, the specific chemistry of the electrodes, and the electrolyte. That sets the potential difference.
So a tiny button cell could have the same voltage as a big D cell if they use the same chemistry.
Exactly. The bigger battery will just last longer. It has more chemical fuel, more capacity. But the voltage, the push, comes from the chemistry.
And how do we get higher voltages, like a 9-volt battery?
Simple. You connect multiple individual battery cells in series. A standard 9-volt battery usually has 6 small 1.5-volt cells linked up inside, positive to negative.
Like stacking them end to end, their voltages add up.
Precisely. 6 times 1.5 volts gives you 9 volts total.
And back to the lemon battery you mentioned, powering an LED. Why an LED specifically?
Because LEDs, light-emitting diodes, are incredibly efficient. They need very little power, very little current to light up. A lemon battery produces such a tiny amount of power
That it probably wouldn't light an old-style incandescent bulb.
Almost certainly not. But an LED, yeah, you can often get a faint glow, proving the principle. It shows even small chemical power can do work.
So, wrapping this up, it's amazing how we've got these two fundamentally different ways to get electrons moving.
It really is. Mechanical motion, spinning coils, and magnetic field.
Right, the generator principle.
And then these carefully controlled chemical reactions inside batteries.
Both achieving the same goal.
Yeah.
Creating that flow of electrons that powers everything.
Yeah, it all comes down to understanding and harnessing electromagnetism, in the case of generators, and electrochemistry, for batteries. These core principles are behind so much technology. Knowing how they work is, well, it's powerful knowledge.
Absolutely. Makes you appreciate the ingenuity involved. So, thinking about these two paths, motion and chemistry, it makes you wonder, doesn't it? What new ways to generate energy might pop up if we start blending these ideas more? Or maybe reimagining them completely? What hybrid approaches could emerge? Something to think about.